In this video, I'm going to get into molecular orbital theory proper. And so in the last video, I talked a bit about hybridization, but in molecular orbital theory proper, we don't talk really much about the hybridization of orbitals. Instead, we talk about the linear combination of atomic orbitals. So you may have seen the abbreviation LCA. That stands for linear combination of atomic orbitals. And so we have our molecular orbital psi here, and it is a linear combination of these atomic orbitals, which are the phi's. And then these C coefficients here sort of tell us how much contribution that atomic orbital is giving to the molecular orbital. So the molecular orbitals form when the atomic orbitals overlap. So the electrostatic force between the positively charged nuclei and the negatively charged electrons hold the atoms together. And so we can kind of think about it. So if we have sort of the nuclei right here, then we have our negatively charged electrons. So if we have this negatively charged electron on this atom here, if we're going to that nucleus there, and this one here going to that nucleus there, there is going to be some attraction to the different nuclei there. And so that's going to sort of hold these things together. Because remember, in reality, the electrons are in sort of a cloud around here. And so when the clouds sort of overlap like this, the electrons from this atom right here will be attracted to that atom right there and vice versa. And so we have three conditions that lead to bonding here. So the first is that the symmetry of the orbitals have regions with the same sign. So the phi from one atom and the phi from the other one. And those overlap as I was talking about up here. So the energies of the atomic orbitals are similar. And so kind of a rule of thumb, it's usually within 12 electron volts. They have to be, the orbitals from atom 1 and atom 2 have to be within 12 electron volts of energy in order to form a bond with each other. So the distance between the atoms is short enough to have good orbital overlap, but far enough away that the nuclei repulsion isn't too high. And so we can look at that using this Morse potential here. And you may have also seen, I think it's called the Leonard-Jones potential, which looks very similar, but I'll be talking about the Morse potential here. And so this is what that potential looks like. And so down here, where the potential is the lowest, is sort of the distance that the two atoms, and in this case is talking about two hydrogen atoms, that's going to be sort of where it's most stable, where out here we have these attractive forces pulling them together. So there is this increase in energy because you're sort of trying to pull things that are attracting each other away from each other. And so you're going to feel sort of a resistance against that as they want to sort of go down to the most stable state here. Then as they get too close together, so as we come towards this axis right here, which you can think of as the nucleus, then the repulsive forces of the two atoms' nuclei are going to increase. And we see that this actually sort of asymptotes up towards infinity as they get closer and closer together. Uh, you know, this Morse potential is obviously kind of a way of sort of approximating this, because we we know for instance, that if two nuclei come close enough together, they will actually attract each other through the strong nuclear force. But I won't be talking about that here. If we are just thinking about the electrostatic force, then the repulsion will sort of go to infinity as the two nuclei get closer and closer together. And so we need it to be sort of close enough that we have the electrostatic attractive forces here, but far enough away that we don't have these repulsive forces here. So each hydrogen atom, so we're kind of using the hydrogen atom as our model here, has a 1s orbital. And so we can call their wave functions. So the phi a here is the 1sa and the phi b here is the 1sb for atoms A and B. We then have two possible linear combinations of the atomic orbitals, which we have right here. And so this, we see we have the plus in it, and then this one here, we are subtracting them. And so these are the two possible atomic orbitals, as I said. And so the n here is a normalization factor, and I'll actually talk about that more in future videos when I actually get sort of dig down deeper into this idea of like the linear combinations of atomic orbitals, and in particular the symmetry adapted linear combinations and things like that. But that will be a future video. For now, just know that there is a normalization factor there. And so then these C coefficients here also, so when we have two atoms that are the same, then these Ca and Cb will be equal to each other, and they will both be equal to 1. And so we can just assume those are 1 because they will both have sort of a 100% contribution to the molecular orbital. And so the one with the subtraction here gives us this antibonding orbital because, well, you can kind of think about it like we have a function that looks like this, and then a function that is the negative of that, which would look like this. And so if we bring those together and overlap them, then we have something that looks like this. And this part here will subtract out that part there, and we end up with something that looks more like that. So there is this sort of there's this node between them here where there is 0 wave function because we are subtracting them. So that's why we get this node here. But if they are the same, then we actually get, so we'd be adding something that looks like this. And so if when we put those together like this, then we would end up with something that's, stronger in the middle like that. And so we actually get something that is sort of constructively interfering right there. And so that's why you need the two phases of these orbitals to be the same sign, because we need those to sort of constructively interfere with each other. And so that is what is going on when we are using this plus version of the linear combination, where the negative version is the antibonding molecular orbital. And so we can look at this a little bit here. So if we have our 1s A here, then we have this antibonding orbital like this, which we denote with a sigma star like this. And then the bonding orbital, where they do overlap, is a sigma right here. And this should actually be the same color as this one here. So I will fix that in the lecture notes, which will be linked to in the description down below. So I mean, I guess I could even fix it right now while we are looking at it right here. So it should look something like that. So yeah, these two things should have the same sign, and so these should overlap with the same color like that, which I do have going on here with the p orbitals. And so what I'm showing here too is we're using this pz here. And so in molecular orbital theory, we usually define the z-axis as the one that that is sort of connecting the two atoms. So we have our two atoms like this, and we sort of define the z-axis that way. And so then we could define, I think oftentimes it's the y-axis sort of sticking out of the screen and the x-axis sticking up that way. And so the z-axis is the axis that sort of intersects both atoms like that. And so that's why I have the PZ there like that. So the other thing to notice too, I have here these C2 symmetry here. And so it's actually the case that a PZ orbital and an S orbital have a C infinity, symmetry, because you could sort of turn this around any amount here. So any sort of, delta amount here. So we could say delta amount here, and you would get the same thing. But these C infinities and the D infinities as well. So the D infinities are very difficult to work with, and so what we do is we actually sort of take into account the fact that, so we have our, say we have our PZ orbital there, but we also have our PX orbital and our PY orbital. And so with these sort of sticking up on here, we actually get a C2 symmetry here, because we can sort of rotate that 180 degrees to get back to the same. So if this is the PY here, then we would get back to the PY after a 180 degree turn. And I'll talk a bit more about this in the future. But for now, just know that that is sort of a simplifying thing that we can do, is sort of take these C infinities and turn them into, so we can turn the C infinity V into a C2V, and we can take the D infinity V and turn that into a D2V. Symmetry group there, instead of having to work with these complicated infinity groups. But anyway, so we have the molecular orbitals from the 2p atomic orbitals, and so we see that we have the anti-bonding up here at the top, where we end up with this node here. And then the bonding, these two things come together to sort of constructively interfere and reinforce each other and form that bonding orbital. And we can do the same thing with the PX and the PY. And so this, so we see here, so yeah, the X is pointing up and the Y out. I think so this should have been a PX right there. But anyway, we have the PX's sticking up and down, and so those can form these pi bonds, and the PY sticking in and out of the screen can form these pi bonds. But we can also get these anti-bonding pi bonds here, and those will be denoted with a pi star like this, where the pi bonds have the pi here. And so this is just kind of showing, so these sigma bonds, so we can form these with the d orbitals here. So we have a d orbital right here, and we see that these can have the correct symmetry to form a sigma bond right here with, say, an s orbital, or with a pz orbital, when we have the z defined as going through all of the sort of atoms involved in the bond. They can also form pi bonds like this with, well, they can form it with p orbitals, but they can also form it with other d orbitals, which is what I have shown here. So the dz squared here can form sigma bonds. The dyz and the dxz here can form these pi bonds by having these lobes here interact with each other. And so we can also get these delta bonds, which I'm not actually going to talk about too much, but we can see that we can have these sort of four-fold interactions here with these d orbitals. All right, so now, and this is something we'll be using a lot, are these molecular orbital energy diagrams. And so we are bringing the atom A here and the atom A here uh, together, and so these have equal energies. And so on the left here we have the atomic orbital for atom A, and we have the atomic orbital for this atom A. And so maybe we'd have electrons in here like this, and then in the middle here is where we have the molecular orbitals. And so we see right here, this will be the sigma bond, and this will be the sigma star bond, the antibonding up there. And so we see the antibond has higher energy than the atomic orbitals, where the molecular orbital has lower energy than the atomic orbitals. And so when we form bonds between atoms, we are actually reducing the energy. So I think people have the kind of have this idea that like a bond is something that is energy, that it has like that there's like this bond energy, but in fact a bond is something that has lower energy. So in thermodynamics, systems are always trying to go to lower energy, and so something that has higher energy is going to be less favorable, and so it's going to try and get to something that's lower energy. So if you get into things like kinetics and thermodynamics, you run into things like the activation energy, and so the energy of the reaction would look something like this. And so the sort of initial state where we have the reaction, the reactants, and the products here, the products are going to be lower energy here than the reactants, but you do need to put energy in for this activation energy. But anyway, that's kind of getting a little off course here. The idea I want to sort of bring home, though, is that the bonding molecular orbital is going to be lower in energy than the atomic orbitals, and the antibonding is going to be higher in energy. And so if we actually brought these together the way I have it, where we have 2 electrons here and 2 electrons here, we'd end up with 2 down here and 2 up here. And as I'll talk about here in a little bit, when we have 2 in the bonding and 2 in the anti-bonding, then they sort of cancel each other out, and we don't actually get any bond going on. And so that's why you actually often see it where the if we had, say, for instance, so if we sort of got rid of an electron from each side here, so that each side just has 1 electron, then you would actually just end up with 2 down here, and you would get a bond going on. So that's why you have these sort of unfilled shells that want to sort of form bonds with each other. So these subshells that have just a single electron in it wants to bond with something that has just a single electron in it. Or even conversely, if we get into like the frontier molecular orbitals, so if we had something that looked like this, where we have, well, this should actually be a spin up, then this one, which would be like a lone pair, and this sort of empty molecular orbital or atomic orbital here could come together and form a bond. But we also see here we can have unequal energies. So if we have some atom A and some other different species, some other different element B here, where B is, say, something that's a little bit more electronegative, then it has a lower atomic orbital here for B than the A, which has this atomic orbital of a higher energy here. And so coming together, once again, we have the molecular orbitals. So this is the sigma, and this is the sigma star right here, where the sigma, again, is going to have a lower energy, the sigma star a higher energy than the atomic orbitals. And then we can get into very unequal energies here, where we have the atomic orbital for B and the atomic orbital for A. They come together and form the molecular orbitals here. And so if these energies get far enough away, you're going to have very little overlap with them, because remember, that's one of the things that we have to have if we want a bond to form, is that the energies have to be close enough together. And what actually happens is when the energies sort of get far enough away, you end up getting an ionic bond. And so you just end up sort of moving the atomic orbitals from here over to here, and you just form sort of a crystal lattice using the electrostatic forces. But I'll get into that a bit more in a later video. And so these are kind of the three basic molecular orbital diagrams that we will be using. And so we can look at an example here. So this is something, so we have the 1s atomic orbitals here, and so if these are filled, then so we'd have the atomic orbitals like that here. And so these come together, so we have a sigma and then the sigma star. Those cancel each other out. Then we can do the same thing for the 2s here, where we have the atomic orbitals here. They come together, form these molecular orbitals, and we have the sigma and the sigma star filled, so those cancel each other out. And then we sort of move up to the 2p here, so the 2p, which has three atomic orbitals here, and so these form the sigma bonds with the pz orbitals, and then the pi bonds with the py and the px orbitals. And we see that these are only adding electrons into the bonding orbital, so the sigma and pi, where the pi star and the sigma star are going to be left empty. And so this would actually be a triple bond right here, because we have this bond, and this bond. And so this is actually the molecular orbital energy diagram for nitrogen, so N2, which if we know from our sort of Lewis dot structures, so we have something that has a triple bond like that. And so this is where that triple bond comes from. And so if we had something with oxygen, then we would actually start adding electrons up here, and we'd sort of lower that bond order. And so that's why O2 is sort of looks like this, so it only has a double bond. And so we'll actually look at that here in a second. So one other thing I wanted to point out, so we would expect that the sigma bonds would be lower energy than the pi bonds, that these would be sort of flipped around, that we would have the sigma down here and the pi sort of up here. And I'll talk about in the next video that we actually have what's called orbital mixing. And so for some of these, this actually gets flipped, where the pi bonds are lower energy than the sigma bonds. But when we get to oxygen and fluorine, that actually then flips back around again. But like I said, I'll talk about that more in the next video. For now, we're just looking at the fact that when we don't have these antibonding up here sort of canceling out these bonding, then the sort of number of bonding sort of minus the number of antibonding is the bond order. And actually, I'll talk about that down here. So here is actually looking at the F2 and the O2. And so once again, so here we see that the sigma for the F2 and the O2 is actually lower than the pi bonds. But the thing I wanted to point out, so this isn't showing the 1s orbitals, but those would also be canceling out. But we have the 2s on each of these canceling each other out, so the sigma and the sigma stars canceling each other out. Then in the fluorine, we have the sigma pz, we have the pi for the px and the pi for the py here, but then we have the 2px and 2py antibonding here. And so those are actually canceling out these pi here. So that's why F2, so F2 from our Lewis structures only has a single bond. So our Lewis structure looks like that. So we have a single bond. And so the other thing to notice here, so the number of electrons here in the atomic orbitals plus the number of electrons here in these atomic orbitals all have to be brought into the molecular orbital. So we have 2, 4, and 5. So we have 10 total. So we have 2, 4, 6, 8, and 10 here. And so we just have to fill those up starting from the lowest energy to the highest energy. And so then we just sort of take, whatever it has bonding and anti-bonding filled, those cancel each other out. And so we only have this sigma bond here from the 2pz in our diatomic fluorine. Then the thing to notice for oxygen is that we do the same thing. We add our atomic orbital electrons into the molecular orbitals. And what we see is we have these 2 lone electrons in these antibonding orbitals. And so we still have sort of 2 electrons up here, which cancels out sort of one of these pi bonds, which is why oxygen still has a double bond character, because we have the sigma bond. We sort of have one of the pi bonds going on here. But we have these 2 electrons, these 2 lone electrons in these antibonding orbitals. And so famously, this is why oxygen is actually paramagnetic. And so if you take like liquid oxygen in like a little vial and sort of put it in a magnetic field, it will actually move. So we have our magnet here. It will actually move towards our magnet here. So oxygen is actually magnetic, and that's because it has these 2 unpaired electrons here, giving us sort of a total spin on our oxygen molecule there. So yeah, the bond order is calculated this way. So we take half times the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So for fluorine, we have the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. So we have in bonding orbitals, we have 2, 4, 6, and 8 here. And then we have 6 here in anti-bonding. So we have 2, 4, 6 in anti-bonding. You could actually just also add the ones for the 1s orbitals, but it's not going to change anything because we just move this to 10 and this to 8, and we would still just get 2 over 2, which is just a bond order of 1. And so we'd only end up with this single bond right here. So for oxygen, it's 8 minus 4. So we have the 2, 4, 6, and 8 bonding. And then for the antibonding, we have the 2 and then the 3 and 4 here for the antibonding. And so it has a bond order of 2. And so that's why we have the double bond on it. But yeah, anyway, that is sort of the introduction, as I said, to molecular orbital theory and sort of these molecular orbital energy diagrams, which will be used quite a bit in the next few videos. As I talk a bit more in the next video, I'm going to talk about the homonuclear diatomics. So, things like the lithium-2 and beryllium-2, carbon-2, nitrogen-2, oxygen-2, fluorine-2, neon-2, and so you'll actually see why things like neon don't are the noble gases and don't actually form bonds, and that comes right, you can see that in molecular orbital theory. Then in the video after that, I'm going to talk about heteronuclear diatomic molecules, which are things where you have atoms of 2 different kinds. Then I'll get into some sort of larger molecules, things like carbon dioxide and water and things like that, and we'll see that we have to do something a bit different for those in molecular orbital theory. Then the video, I'll probably spend a few videos after that talking about like electron spectroscopy, which is how we find like the ionization energies. And I'll talk about like the atomic and molecular orbital terms that you may have seen, which are like the capital letters that have some number down here and then some number up here, and things like that. You may have even seen it. Well, when we get into molecular orbitals, you see it with like a U or a G down there. You might see it with like a plus or minus up there, so U or G. Then it'll have some number up here. But anyway, I don't want to get too ahead of myself, so I'll talk a bit about that. Then after that, I'm going to sort of dig down deeper into things like the symmetry adapted linear combinations and these symmetry adapted group orbitals and things like that. And that's where a lot of the group theory that I talked about in my group theory videos will really come into play, and we'll use things like the projection operator and stuff like that. But anyway, I hope you found this video helpful, and I will see you in the next one.